A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
You know, there is something deeply surreal about watching high-definition footage of a missile interception taking place in the literal vacuum of space. It looks like a silent flickering star suddenly blooming into a cloud of debris, and then it is just gone. It is a visual that feels more like science fiction than modern reality, yet it is happening with increasing frequency. Today's prompt from Daniel is about that exact visual paradox, specifically regarding the Aero Missile Defense System. He has actually launched a new open-source website called promisteny.com that tracks data on Iranian munitions and the interceptors used by Israel and the United States.
I have been looking at that site all morning, Korn. It is a fantastic resource for anyone who wants to move past the headlines and actually look at the hardware parity. One thing Daniel pointed out, which is what we are diving into today, is the physical asymmetry of the interceptors themselves. When you see an Aero 3 launch, there is this massive pillar of fire and smoke, but the actual kill vehicle, the part that does the work once it leaves the atmosphere, is surprisingly small. We are talking about something roughly 7 meters tall in its total interceptor configuration, but the diameter is only 70 centimeters wide.
It really does look tiny compared to the massive ballistic missiles it is sent to hunt. You see these shots of an Iranian Shahab 3 or a Khyber Shakan, and they are these hulking, intimidating cylinders of metal. Then you look at the arrow, and it is basically a very expensive, very fast needle being thrown at another needle thousands of kilometers away. I am Korn, by the way, for anyone joining us for the first time.
And I am Herman. It is good to be back in the booth. Daniel's question hits on something I think a lot of people overlook when they watch these conflict videos on social media. How do you take the processing power of a modern data center, the sensory suite of a high-end satellite, and the propulsion requirements of a spacefaring vehicle, and then crush all of that into a tube that is narrower than a standard office desk?
It is the ultimate engineering packing problem. If you look at the history of missile defense, the older systems were massive because the electronics were massive. You needed literal vacuum tubes or early discrete transistors that took up huge amounts of volume. But the Aero system represents this shift toward what I call engineering density. Herman, when we talk about fitting a supercomputer into a 70-centimeter tube, what are the primary hurdles there? Is it just about making the chip smaller, or is there more to it?
Making the chip smaller is actually the easy part, believe it or not. We have been doing that with smartphones for decades. The real nightmare in a defense context is radiation hardening and thermal management. In a consumer laptop, if your processor gets too hot, a little fan kicks on and blows air across a heatsink. But the Aero 3 operates in the exo-atmosphere. There is no air. You cannot use convection to cool your electronics.
Right, because in a vacuum, heat has nowhere to go. You are essentially trapped in a thermos.
That is a perfect analogy. If you pack a high-performance system on chip or SoC into a tight space and run it at full tilt to process radar data and infrared imagery in real time, it generates an immense amount of heat. Without air to carry that heat away, the electronics would literally melt themselves in seconds. So, the engineering density Daniel is asking about is not just about the size of the components, it is about the exotic materials used to conduct that heat away from the core and into the structure of the missile itself, which acts as a giant heat sink. They use things like beryllium alloys or specialized carbon composites that have incredible thermal conductivity.
And I imagine they are moving away from discrete components toward these integrated ASICs, or application-specific integrated circuits. Instead of having a board for navigation, a board for communication, and a board for sensor fusion, it is all being baked into single pieces of silicon.
That is exactly the trend. We are seeing a move toward radiation-hardened ASICs that can survive the intense electromagnetic environment of high-altitude flight. When these interceptors are flying, they are being bombarded by cosmic rays and potentially the electromagnetic pulse from other nearby explosions. If a single bit flips in the guidance computer because a stray proton hit a transistor, the missile misses by a mile. That is what we call a single event upset. To prevent that, you have to build in massive redundancy. You have multiple cores doing the same calculation and voting on the result. Fitting 3 or 4 redundant systems into that 70-centimeter diameter is where the real wizardry happens. It is like trying to fit 4 separate brains into one skull and making sure they all agree on where to turn.
It is funny you mention the voting system. It makes the missile sound like a little democratic committee hurtling through space at Mach 9. But let's look at the physical layout. You have the booster stage, which is the big pod everyone sees on the news, but then that drops away. The pod Daniel is talking about, the 7-meter interceptor, is effectively the kill vehicle and its immediate propulsion. How do they decouple the guidance package from the propulsion so efficiently?
The architecture is very modular. The front section is almost entirely dedicated to the seeker head, which usually involves a dual-band infrared sensor, and the guidance computer. Behind that, you have the divert and attitude control system, or DACS. These are tiny, high-pressure thrusters that allow the missile to dance in space. Because there are no wings to provide lift in a vacuum, you have to use pulses of gas to change direction. The miniaturization of those thruster valves is just as impressive as the electronics. They have to respond in milliseconds with extreme precision. If you are off by a fraction of a degree, the kinetic energy of your movement will carry you past the target before you can correct it.
It reminds me a bit of the miniaturization we have seen in the CubeSat world, where universities are fitting entire scientific laboratories into boxes the size of a loaf of bread. But a CubeSat doesn't have to survive a launch where it is pulling 30 or 40 Gs of acceleration.
A CubeSat is a delicate instrument. An aerial interceptor is a delicate instrument wrapped in a tank. The structural integrity is a huge part of that engineering density. Every gram of weight you save on a bracket or a casing is a gram you can use for more fuel or a better sensor. They use a lot of carbon fiber composites and specialized alloys that are incredibly stiff but very light. The goal is to maximize the mass fraction of the propellant while keeping the brain of the missile as protected as possible. We talked about this a bit in episode 997, where we discussed the distributed architecture of the system. The missile isn't working alone. It is part of a human shield network that includes the Green Pine radar and the Citron Tree Battle Management Center.
It is a fascinating transition from the analog-heavy systems of the Cold War to these digital-first software-defined interceptors. I mean, back in the day, a missile was basically a big engine with a primitive clock inside. Now, it is a flying sensor platform that is constantly re-evaluating its mission parameters mid-flight. It is essentially a flying data center.
And that leads directly into the second part of Daniel's prompt, which is the physics of the interception itself. This is the part that really blows people's minds and is often misunderstood on social media. It is about 15,000 miles per hour. At that speed, you could travel from New York to Los Angeles in about 10 minutes. At those velocities, the kinetic energy involved in the collision is far greater than the chemical energy you would get from an equivalent weight of high explosives. When two objects collide at those speeds, they do not just break apart.
Which means there is no explosive warhead at all. It is just a very high-speed car crash in space.
It is a very high-speed car crash where both cars are moving at several kilometers per second. To give you an idea of the energy involved, we have to look at the formula for kinetic energy, which is 1/2 mass times velocity squared. Well, the house analogy is good, but it is more like two high-speed trains colliding head-on. You do not need to put dynamite on the front of the train to ensure it is destroyed. The energy of the motion does all the work. This is why the arrow can be so small. Since it does not have to carry a massive explosive warhead and all the fusing and safety systems that go with it, the engineers can make the kill vehicle much lighter.
I remember we touched on this a bit in episode 705 when we talked about the science of the multi-layered shield. The closing velocity is just staggering, but that puts an incredible amount of pressure on the guidance system. If you're using an explosive warhead, you just have to get close. You have a blast radius or a fragmentation sleeve that can compensate for a little bit of error.
It is about 25,000 kilometers per hour. At that speed, the materials don't even behave like solids anymore during the impact. They behave like fluids. It is often described as trying to hit a bullet with another bullet, but that actually undersells the difficulty because bullets do not actively try to maneuver or use decoys. The arrow's brain has to distinguish the actual warhead from the spent rocket stages or any decoys the enemy might have deployed.
Daniel asked how it is physically possible for a small interceptor to destroy a much larger missile. I think the billiard ball analogy works well here. If you have a heavy bowling ball rolling toward you and you hit it with a small marble moving at the speed of sound, that bowling ball is going to shatter or at least be knocked completely off course. This is where Daniel's point about engineering density comes back around. The reason the electronics is so dense is that the mission requires a level of precision that was physically impossible 20 years ago.
The precision required for head-to-kill is what makes it so difficult. If you have an explosive warhead, you only have to get within 30 or 40 meters of the target. And you have to do it all while the interceptor is undergoing massive g-forces. When those divert thrusters fire, they are putting immense stress on the airframe and the internal components. If a single solder joint fails, or a sensor lens shifts by a fraction of a millimeter due to the vibration, the whole mission fails. The reliability required for these systems is just staggering. We're talking about components that are rated for space-grade environments, which means they have to handle radiation, vacuum, and temperature swings of hundreds of degrees.
I also find the vacuum factor interesting. Daniel asked how this works in the vacuum of space. In the atmosphere, an explosion creates a shock wave that does a lot of the damage. In space, there is no air to carry a shock wave. Does that make the kinetic impact even more important?
It makes kinetic impact the only reliable way to do it. If you tried to use a conventional explosive in space, you would get a flash of light and some shrapnel, but without an atmosphere to create a blast wave, the destructive radius is much smaller. You would basically be hoping a piece of shrapnel hits something vital. By using a direct hit, you ensure that 100% of the interceptor's energy is transferred directly into the target. It is the most efficient way to neutralize a threat in the exo-atmosphere.
It also avoids the problem of unintended damage on the ground, right? If you blow up a nuclear or chemical warhead in the upper atmosphere with a big explosion, you might disperse that material over a wide area, but with a kinetic kill in space, the sheer energy of the impact tends to pulverize the target, and much of the debris burns up upon re-entry. You don't want to just knock it off course. You want to vaporize it so that any debris that enters the atmosphere is small enough to burn up.
It is a very clean, albeit very violent, way to solve the problem. When you hit a warhead at 7 kilometers per second, the chemical components of the explosives inside that warhead are often rendered inert or destroyed before they can even detonate. You are essentially dismantling the threat at the molecular level through sheer kinetic force.
It is interesting to think about the asymmetry here. If it had to carry a 1,000-pound high explosive charge, it would be a much slower, clumsier vehicle.
The mass of the interceptor is actually a liability in some ways. The heavier it is, the more force you need to change its direction. By keeping the kill vehicle small and dense, the engineers at Israel Aerospace Industries and Boeing have created something that can pull maneuvers that would be impossible for a larger craft. It is the difference between trying to turn a semi-truck and a high-end sports car. In the vacuum of space, where you only have a limited amount of propellant for your divert thrusters, being lightweight is a massive advantage.
I find it interesting how this mirrors the broader trend in military technology, where hardware is becoming a commodity, and the real value is in the software. The Arrow missile is essentially a very sophisticated delivery mechanism for an algorithm. The physical impact is just the final step in a long chain of data processing.
We are seeing this across the board. Whether it is drones, missile defense, or even electronic warfare, the physical platform is almost secondary to the logic gates inside the chips. This is why Daniel's work with PromisedAny.com is so relevant. When you look at the data, you start to see that the missile gap isn't about who has the biggest rockets anymore. It is about who has the best sensors, the lowest latency, and the most robust guidance code. We did a deep dive on the Green Pine radar back in episode 1000, and it is the unsung hero of this whole process. Without that long-range eye telling the arrow exactly where to look, all that miniaturized electronics inside the missile would be useless.
The integration of the whole system is what makes it work. You have the radar on the ground, the battle management center, and then the interceptor itself. They are all talking to each other in a closed-loop system. The arrow isn't just a fire-and-forget weapon. In the traditional sense, it is an extension of a much larger planetary defense network. It is a system of systems.
And that brings us to the takeaways for today. If you are a listener looking at the conflict between Iran and Israel, it is easy to get overwhelmed by the sheer number of missiles being discussed. But Daniel's site, promisedeni.com, breaks it down into these manageable data points. What should people be looking for when they evaluate these systems?
One of the biggest things to look for is the interception rate versus the number of munitions fired. But even more than that, look at the altitude of the interceptions. If you see interceptions happening in the exo-atmosphere, that tells you the arrow system is doing its job. It means the threat is being neutralized before it even reaches the dense layers of the air. It is a sign of a very high-functioning, high-tech defense layer. It also means less risk of collateral damage from falling debris over populated areas.
I think it also helps dispel some of the propaganda on both sides. When you understand the physics of hit to kill and the engineering constraints of these interceptors, you realize that this isn't magic. It is incredibly hard work, and it doesn't always go perfectly. There are failures, there are misses, and there are debris issues. But seeing the data aggregated in one place allows for a much more sober analysis of the geopolitical situation. It moves the conversation from who is winning to how does the technology actually perform.
It is the shift toward a data-first approach to conflict. Instead of just watching a video of a flash in the sky and guessing what happened, we can look at the telemetry, the known specs of the Arrow 3, and the estimated trajectory of an Iranian Shahab missile. It turns a chaotic event into a solvable physics problem, and that is really the takeaway for today. The engineering density Daniel asked about is the result of decades of pushing the limits of what materials and silicon can do.
We are living in an era where the shield is becoming just as technologically sophisticated as the sword, if not more so. The miniaturization of these systems is what allows them to be effective. If they were bigger, they would be slower. If they were slower, they would be useless against the modern generation of ballistic threats. It is a race between the speed of the missile and the intelligence of the interceptor.
And right now, the intelligence seems to be keeping pace. I want to encourage everyone to head over to promisedeni.com and check out the work Daniel is doing there. It is a great example of how technical literacy can be applied to real-world events to provide clarity. It is about taking the mystery out of the pillar of fire and understanding the needle inside.
It is definitely worth a look. The visual asymmetry he mentions is a perfect starting point for understanding how modern warfare has moved into the realm of high-precision engineering. It is not about the size of the explosion, it is about the precision of the impact. As we move toward the future, we are likely going to see even more miniaturization. We might even see a shift toward directed energy systems like the iron beam, which takes this to the logical extreme.
Right, the iron beam. Instead of a 7-meter interceptor, you have a beam of light moving at the speed of light. No mass, no propellant, just pure energy transfer. But that is a conversation for another day. I think we have given the listeners plenty to chew on regarding the arrow and the physics of space-based defense.
It really is a wild world. Before we wrap up, I want to give a big shout out to our producer Hilbert Flumingtop for keeping everything running smoothly behind the scenes. And a huge thank you to Modal for providing the GPU credits that power this show and help us process the research that goes into these episodes.
We couldn't do it without them. This has been My Weird Prompts. If you are enjoying the deep dives into engineering and tech, a quick review on your favorite podcast app goes a long way in helping other people find the show. You can also find us at myweirdprompts.com for the full archive of over 1,100 episodes and all the ways to subscribe to our RSS feed.
We will be back soon with another prompt from Daniel or whoever else decides to send us down a rabbit hole. Until then, keep looking at the data.
See you next time.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My weird prompts, that's the flows from slow